Hi, everyone. This is Andy Frank, your moderator. It is my pleasure to introduce you to panel 5B, Heat Pumps and Associated Building Retrofits. First and foremost, thank you to all of our sponsors and ally members for their support of the Energy Efficiency as a Resource Conference, as well as ACEEE more generally. I'm really excited to talk about all things heat pumps today, and we've got an amazing panel to do that with you. Each speaker is going to talk for about 10 minutes, and then we're going to dive into some questions that I've prepared, but also really want to make sure that we get as much of a lively panel as possible. So I really encourage everyone to ask as many questions as you can, and we'll get to all of them that we're able, either during the main part of the session or in the after Zoom discussion. So please use the chat box on the right-hand side of your screen to ask questions of the presenters. As moderator, I will share your questions with the speakers once all the presentations have been made. And again, if we don't get to your question, please join us for 20 minutes of chat and discussion on the Zoom platform immediately following the session. The Zoom link will be posted in the chat later during the session. So please refrain from using the chat for any other dialogue other than asking questions, and there'll be another forum for us to have a more robust discussion. Please also make sure to check out all of the options on the left-hand side of the app where you can connect with other attendees, engage in our game to possibly win a free registration to the 2023 Philadelphia Energy Efficiency as a Resource Conference. You can visit the resources section to download a PDF of the program and the Zoom links for all the concurrent chats and discussions. Lastly, we ask everyone to complete the conference evaluation form found in resources. Anyone who completes the evaluation and includes their name and a testimonial will receive a discount to attend that next Energy Efficiency Resource Conference. As a reminder, all presentations that you're going to see today will be available for on-demand viewing within a few days on this Engagement Hub, and presenters' PowerPoints can be found on their page in the program participants section. So with that, I'm excited to introduce our panel to you today. I'm going to give longer introductions with each of them when I'm setting them up to give their presentation, but want to give you a preview. Today, first speaking is going to be Josh Quinnell from the Center for Energy and the Environment. He's going to be speaking about high-performance envelope upgrades and why they're such an essential measure related to cold climate electrification. Next up, we have Jim Jarazal from Nicor Gas, and he's going to talk about gas utility strategic collaboration around affordable decarbonization and around specifically gas heat pump technology. And last but certainly not least, we have Lieko Earl from the National Renewable Energy Laboratory, and she's going to talk about the role of DERs, particular electrification retrofits, and community-wide efforts. So basically taking a little bit of a broader look at how heat pumps and their associated benefits can impact the grid. So we have a really great panel. As I mentioned, encourage everyone to put in their questions on the side, and we'll get to as many as we can either during this session or we'll have a great follow-up discussion over Zoom afterwards. So with that, I am really excited to introduce Josh. As I mentioned, he is from the Center for Energy and the Environment up in Minnesota. He is a senior research engineer with 13 years of research experience in the fields of solar energy and energy efficiency. Josh is currently working on grid modernization efforts, including strategic electrification, solar energy deployment optimization, and using efficiency and other distributed energy resources to manage distribution system capacity. Prior to joining CEE, Josh studied thermochemical energy storage at ZAE Bayern in Munich, Germany, and he obtained his PhD in mechanical engineering from the University of Minnesota. So we got a lot of academic firepower here to talk about cold climate electrification and high performance envelope upgrades. So with that, I'm going to turn it over to Josh to take you through his presentation.
All right, thank you, Andy. Today I'm going to bring together two topics that I've been working on for a while, but have finally brought together in sort of one piece of research. And this is cold climate single family envelopes and cold climate electrification via air source heat pumps. So first of all, I just want to say it's been amazing the amount of tension and excitement we've seen over decarbonization via building electrification, especially in a cold climate like Minnesota. That excitement has been building. We're seeing the promise to near-term retirements for all our major coal plants. Our largest utility will soon be 85% carbon free. And everything we plug in soon will may have order of magnitude or greater emissions reductions in their lifetime. But in climate zone 6 and 7, there's only one thing that ultimately matters, and that is space heating load. For example, our single family homes, all 1.6 million of them, use 60 to 80% of their total site energy budget in heating those homes. Cold climate air source heat pumps are a phenomenal opportunity to save 50% or more site energy in all of these homes. In fact, they're so important. They probably are more important than all other measures combined by a factor of 2 or greater. So it's hard to understate how important the space heating load is and the electrification opportunities from heat pumps. But let's talk a little bit about our building stock. 73% of our homes have been built before 1990. And our climate, while it varies between climate zone 6 and 7, it does see some variation. In the southern reaches, we have design temperatures as high as minus 11 Fahrenheit. In the northern reaches, as low as minus 22 Fahrenheit, and even lower. Our climate winter heating load can be defined by heating degree days between about 7,700 and 9,700 statewide. It's important to call out the southeast here specifically. This is where most of our homes are located. This corresponds to the Minneapolis-St. Paul metro area. There's about 1 million homes here. So we've done some modeling, and what are the actual loads on these homes across our climate? Here is a histogram that shows by climate region our design loads on our single family building stock, explicitly those homes built before 1990. The good news is the loads are a lot smaller than we conventionally expect from our rules of thumb. Median load is around 44,000 kBTU. That's just under 4 ton. Meanwhile, we have about 25% of our homes have design loads less than 36,000 kBTU or 3 ton. And then only a quarter of our homes have design loads greater than 5 ton. So when we talk about meeting these loads, we need to look at the heat pumps that are available. I have 3 kinds of heat pumps I'm showing here, a couple of them in both 3 ton and 5 ton capacity. I have what I call the reference tier. These are the blue curves. And I'm showing here capacity as a function of outdoor temperature. We all know by now that air source heat pumps lose a fair amount of their capacity as it gets cold outside. But the reference tier, they're variable speed cold climate heat pumps. They're strong performers. They maintain fairly good capacity down to 5 Fahrenheit. They unfortunately lose capacity below that. We have another kind of heat pump called the Capacity Champ. This is essentially the highest capacity maintenance we can find currently in the NEEP air source heat pump database. They do a better job of maintaining capacity at cold temperatures, and they still have strong performance in terms of CO2. As sort of a upper benchmark, I've also added a fictional transcritical CO2 heat pump, something we might aspire to in the future, although I know of nothing like this now. This system meets 90% of its capacity at minus 25 at a COP of 2, so a very high performance standard. So now let's look at what these systems can do when we pair them with our building stock. Well, they don't do very well. This is our percentage of existing single-family homes, again, those built before 1990, whose design loads can be met by these various pieces of equipment. Our fictional system can meet the heating load in 4 out of 5 homes. That system does not yet exist. It may never exist. If we look at our best system today, the 5-ton Capacity Champ, that can meet design load in about 40% of our existing building stock. All the other systems fare significantly worse. So what's the takeaway here? Well, we might be saved one day by ultra high performance heat pumps, or maybe we just need auxiliary heat. And here I'm distinguishing auxiliary from backup. We often call it backup heat with respect to air source heat pumps. When it's electric resistance, I like to call it auxiliary power. Our heat pumps are still going to run in cold temperatures. They just can't put out the capacity that our buildings need. So we can supplement that with existing electric resistance. For example, a plenum heater that boosts supply temperatures as they tend to fall in cold weather. This might not be such a big deal because this is our design condition. We rarely need that capacity, maybe 50 hours a year or less. This chart shows basically how much of that auxiliary heat we need depending on the systems we install. And the bottom line is even this fictional high performance system needs about 3 kilowatt of median capacity across the heating load. And all the other systems need more, 5, 7, 10, up to 15 kilowatts of auxiliary electric resistance. So what does this do to our peak load and the load we're going to eventually ask to be put on the grid? Well, it doesn't look that great. Here I'm showing the peak load. This is the auxiliary electric resistance plus the output of the heat pump, the input of the heat pump. Today, if we look at our best case, which is our capacity champ 5-ton system, paired with the necessary auxiliary heat, we're looking at a median peak load of around 8.7 kilowatt. This is not great from a supply side perspective. It's probably 2 to 4 times the summer peaking we get from residential air conditioners. Even if we look at this future transcritical system, that's still going to be on the order of 6 kilowatt or greater median peak. And again, this is the median of a population of over 1 million homes. Unfortunately, this doesn't quite get it either. We have our design condition, but then we have our peak loads. We have our cold snaps, our what they now call polar vortices. But then generally it just gets real cold a couple days a year in Minnesota. And it gets worse than the design condition. If we look at our annual coldest periods by 1 hour, 8 hour, and 1 day, that's a table in the bottom left. This shows the percentage beyond a design condition or design load we get. You can see that our 1 hour peaks are 6 to 17% greater. As we get to longer periods, though, we get closer to a design condition. Geographically, most of the state is less than the design condition at 1 day. However, I will call out the Southeast. The metro area still is capable of having 24-hour periods that exceed design load by 10%, in which case that 8.7 median peak maybe bumps up to 9.5 kilowatt, which is quite a large load. So to recap, in the middle here, air source heat pumps are extremely promising for decarbonizing what is our biggest building end use. Unfortunately, the majority of our single-family stock needs substantial auxiliary or very substantial backup. Even with today's best and biggest heat pump, even fictional high-capacity heat pumps will drive unprecedented system peaks. And then we have to consider the coldest weather, whether it's the coldest day of the year or the weather events associated with extreme phenomena. And so this might seem kind of dire. It's not, though. Actually, the solution is obvious. It's always been obvious. Maybe you already know from the title of my talk. It's always been about the envelope. Essentially, we need aggressive weatherization. Weatherization has been extremely successful. We need to weatherize to higher standards, and we need to weatherize on significantly larger scale efforts. And in fact, we probably need to go further and consider actually high performance envelopes. We have an extremely demanding climate. Low fuel prices have shielded us from the demands of our climate, but we need to think about things like continuous exterior insulation. There's a lot of opportunities to engage these projects in our existing way of doing things. We also need to talk about windows. We've been dithering about the cost effectiveness of windows now for an entire generation of windows, and it turns out windows are twice as good now as they are in the existing building stock. So we have a model. We modeled a bunch of things. I'd be happy to talk with you at length about that. This is the bottom line on aggressive weatherization. These are the costs on the left and the savings on the right. Weatherization costs on median about $3,900 a home, on average just over $4,000. That gives us savings profile on the right over about 1 million buildings in Minnesota, 15% median savings, 20% average savings, and a long tail of very low hanging fruit, 30, 40, 50, 60% savings. And these kinds of savings show tremendous results. Here is a plot that I am showing again. Previously, I showed you the data in blue, which is the amount of our building stock that can be met with these systems. Once we weatherize our buildings, the yellow bars are what we get. So our fictional system did very well. It does even better once we weatherize our homes. But now with our high-end current capacity champion system, we go from 40% to 3/4 of our building stock can be met at the design condition with the air source heat pump. Our 3-ton and our reference 5-ton are now sitting at 33% and over 40% of our building stock just from aggressive weatherization alone. This also comes with a massive peak load benefit of about 25% reduction in peak load. And by the way, this work is all cost effective today across 1 million homes, according to our application of the current Ben cost framework in Minnesota. But let's not stop there. We got to go one step further and talk about continuous exterior insulation and window upgrades. Showing you the same kind of plot here, looking at how much it buys us on terms of air source heat pump capacity when we install these things. Now we're looking at from today's best systems, upwards of 80 to 90% from the best system. And even our reference system now sitting at nearly 3/4 of the existing building stock can be met at the design condition with an air source heat pump. This weatherization, this continuous insulation, this also tightens up our buildings so we can now seriously consider energy recovery for additional benefits. And the best part of all this is our peak loads are finally coming down to levels that are more similar to what we see today, 3 to 4.5 kilowatt. One final note here about costs. There's a lot of costs going to air source heat pumps compared to conventional systems, and the incremental costs do add up over time. And in most cases, these are not cost effective save except for propane and electric resistance. Most of our state is heated by natural gas, and this is a real issue with cost effectiveness. I did mention that aggressive weatherization is cost effective today against propane, electric resistance, and about 20% of our gas heated building stock. Continuous insulation is almost cost effective. There are hundreds of thousands of cost effective opportunities. Windows continue to be a problem. I'm running out of time, so I'm really moving here. The bottom line, though, is I misled you up front. Air source heat pumps are not the most important cold climate building decarbonization measure. They are the second most important measure. The most important thing for us to do is finally upgrade our building envelopes, reduce our heating loads to a level that we can meet with heat pumps, that we can meet with supply side investments on our grid. And dual fuel applications, which is what we're promoting right now and trying to advance, are the opportunity to enable this. They allow us to keep our fuel heating systems in place, deal with the capacity issues, deal with the peak load issues, while we introduce everyone to heat pump technologies. They essentially will buy us one product lifetime, let's say 16 years, to either develop magical high performance CO2 heat pumps or sort out our envelopes and manage our peak load. Thank you for listening.
Thanks, Josh. Really fascinating presentation, and I'm excited to dive into the Q&A and discussion afterwards. As a quick reminder to everyone, please put your questions into the chat on the side. I see we've got the party started over here. I'm going to wait though until the full presentation is gone, and we'll circle back to the questions. But put them in, and they will not get lost. I promise. So speaking of electrification and gas. Our next up is Jim Jarazal from Nicor Gas. Jim has worked at Nicor for 19 years, close to an even 20, and of that, the last 11 years have been focused on energy efficiency. So this is a topic that he's been really focused on for over a decade. And in fact, Jim started and launched the Nicor Gas Energy Efficiency Program in 2011. Jim lives outside Chicago in Geneva, Illinois, and has been married to his wife for 18 years with 2 children, aged 16 and 14. I grew up outside of Chicago myself, so very much appreciate that. And when he's not staying at home during the pandemic or worried about a teenage driver, as I'm sure we all are, Jim is leading teams to Bangladesh and Calcutta with his wife on mission trips. And also a plug that I wanted to put in for Jim is that his wife's Jim is also his wife's part-time publicist, and she's a recent author, and she has written her first book entitled Life in Psalm, which is available on Amazon. So if you don't get enough of Jim on gas heat pumps, you can check out the full Jarazal family on Amazon. So with that, hand it over to Jim, and he's going to talk more about gas heat pumps and how that plays into the concept of affordable decarbonization.
Well, thank you, Andy, for that kind introduction and for the shameless plug for my wife. But it's an exciting time for the Jarazal family. Thanks so much for allowing me to talk today. I'm going to take an opportunity to talk a little bit about the gas perspective with respect to this conversation. We had really great discussion from Andy, or just a minute, or Josh, I'm sorry, just a minute ago. But I want to talk about how gas heat pumps can play a role in a decarbonized future. Let me see. I am trying to advance my slide. I'm not sure. Is my slide advancing, Andy?
Hey, Jim, no. You need to change your display settings.
Okay. Sorry about that. That's not what I want, though, is it?
There you go.
Is that it? You got it?
Yep. We got it.
Okay. Sorry. Thank you. So very quickly, I don't plan to, get into a deep engineering discussion today, but I do plan to talk a little bit about gas heat pumps. Quickly, what are they? Why they're critical for decarbonization, and then a plan to transform the market and how a number of utilities are working together to do that. very quick non-engineering kind of analysis of what a heat pump does, gas and electric. Basically, you're taking energy from the actual combustion that's occurring in the gas heat pump. This isn't a water heater, for example. You're stealing some energy from the air. Combined together, you get more units of energy than you put in. And of course, you can use different kinds of heat sources like RNG, hydrogen blends, etc., that could play a role in a decarbonized process. There are a number of different products out there. From a residential application, not yet available, but there are commercial units that are available. I'll be talking a little bit about some of these new products that are coming online here in 2023. I will just state that there have been testing that have gone on, pilots for residential space and water heating combi units. They have survived through 2 polar vortexes, and guys, they work. They work really well. This is a picture of a combination gas and water space heating system. They deliver over 100% efficiency. They provide reliable heat, and they interchange well within an existing home. They provide efficiency, like I said, over 100%. They're affordable because you can easily put these into the system. And they present a resilience play, right? When we do have those peak loads that Josh was talking about and strain on the energy systems like we've seen in other parts of the country, these are really important to try and shave off that peak. When I talk about efficiency, I'm talking about, say, a typical furnace 98, 97% AFUE, we're talking about 130, 140% AFUE. From a water heater, 0.62 energy factor, you're talking about 1.2. So you're kind of doubling or almost nearly doubling the efficiency level of these products. Hold on. And when I talk about decarbonization, what do I mean? Well, obviously, this is a step change in usage. If we're reducing usage by half, that's a big impact on just gas usage. When you put a cleaner fuel in there, say RNG, hydrogen blends, you're really starting to talk about a net zero play. And I might mention that the refrigerants used in these devices are very low global warming potential, unlike maybe the electric systems. So what are we trying to do? We need to look at a different way of bringing these products to market. We need to look at market barriers, and we need to kind of get away from the typical approach. I think, most of us in the energy efficiency world, we might just sort of slap a big incentive on the side of it, kick it out the door and say, go and do good. And guess what? Sometimes that works, sometimes it doesn't. And so we need to look at a different way of addressing the market. What are the different aspects that might be issues that we need to overcome? How do we identify those issues, and how do we eliminate those issues so that these products can move? So this is really about eliminating market barriers as we go forward. So what we've done is we've created a collaborative, North American Gas Heat Pump Collaborative. And the purpose of that is to indeed do that, to bring new technologies to the market, get them into the market quick, and make a difference. So this collaboration has an opportunity to create a clear message to the manufacturing market, clear message to other actors in this space, to basically say, we need these products, we need them now. We're going to work together to make it easier to adopt. On this chart, you can see 35% of the gas customers are represented by the current suite of utilities that currently form the North American Gas Heat Pump Collaborative, which is only a year old. And so what are we doing? We're talking about market interventions. We're talking about trying to move this curve up and to the left. So this diagram that you see here, if you just let the market do its own thing, it'll grow over time. That line at the bottom, the light blue line, is kind of like just business as usual. You're just sort of letting the natural baseline go. And maybe if we just kind of apply the typical approach, you kind of get that darker blue line. You sort of increase participation, you sped adoption. But really what we're talking about is supercharging the market, trying to move towards that orange line to increase adoption, the speed of adoption, and really transform a market. That's what market transformation is all about. This collaborative is focused on two products, the gas heat pump water heater and the residential combination space and water heating product. You can see some of the strategies that we're looking at. These are, again, understanding this market, knocking those barriers down, making sure we can intervene appropriately, and see incredible adoption rates that unless we do something, it will take too long. Here's a great example. For the gas heat pump water heater, our goal as this collaborative is to try and capture 10% of the water heating market. That would be about 400,000 units in 5 years. In comparison, when the electric heat pump water heaters were released, it took 10 years to essentially reach something similar to this. And you know, the areas where they had good adoption rates were in the Pacific Northwest, where they applied these very principles, these market transformation approaches. So it's very important that we think about how we're intervening in the market, how we make these things happen. Looking ahead, what has the collaboration got in store? We're forming a nonprofit. As a matter of fact, in the first of the year, we'll be a nonprofit. We plan to continue the investments and efforts as a collaborative to work towards communicating and identifying and telling the story about gas heat pumps. We will continue to work in the initiatives for these two products and probably expand beyond those gas heat pump products. And a little bit of a plug, we have a free webinar scheduled for November 1st, just coming up here in a short period of time. And if you're at all interested in learning a bit more about how we're doing this, if you're interested in becoming part of the collaborative, if you're in the gas space, it could be a combo company or just gas only, we'd love to have you join us. You can certainly email me. My email's on the screen here, and I can connect you to the right folks to get you involved. But we certainly would love to have you do that. I'll just leave you with one thought. I think gas has a role in this fight and climate change fight that we're fighting, the war on climate change. And I think as we evolve and as we start looking at a full picture of how we address this, we don't want to leave gas behind. We don't want to leave gas like the gas regiment back at the fort, kind of polishing the tanks and polishing everything and never getting into the battle. I think they play a significant role, especially in cold climates. They can address some of the issues that Josh was talking about. We can do it affordably. We can add resilience to the play. It's really a win-win for everybody. So hopefully people can take that away as we start thinking through this. The golden age of gas heat pumps, 2023, 24, 25, we will have multiple products in the market. They'll be ready. They'll be accessible. So it's time is now to start planning for them. So thanks for that opportunity to speak today, and I'll just hand it back over.
Thanks, Jim. Really fascinating presentation. And for those of you that couldn't see, which I think at least was me, and I think everyone, Jim's contact information, his email, which again will be in the slides, you'll have access to after the presentations is jjeroza, so JJEROZA at southernco.com. So again, if you want to get in touch with him and you need more information directly. And so thank you, Jim. As someone who grew up with a father who worked at the Gas Research Institute in Chicago for many years, appreciate the focus on innovation and the focus on carbon solutions from the industry. Okay, so. Last up, as I mentioned, last but not least, is Leeko Earl from the National Renewable Energy Laboratory. She is a senior researcher at NREL, the National Renewable Energy Laboratory. She's been at NREL for 12 years and has led field testing efforts for the residential buildings team. So again, you guys are getting really the cream of the crop here on the panel today. And her current research centers around grid interactive building innovations, including home energy management systems, connected and smart appliances, as well as electrification strategies, including in particular retrofit strategies. So with that, I will turn it over to Leeko, and then when she's done, we will dive into some questions of the panel.
Awesome. Thanks, Sandy. I am sharing my slides. Are they up? Yep, they are. Great. So I'm here to give you some highlights of a recent simulation study that our team concluded that looked at a few different approaches to residential neighborhood level electrification. So this is a little bit broader than just heat pumps, but I think still very relevant. So our central research question was this: instead of choosing between traditional energy efficiency upgrades of existing buildings, so what we think of as conventional retrofits, so instead of choosing between that and the integration of photovoltaics and other distributed energy resource technologies, what are the most promising combinations of both conventional energy efficiency retrofits and more advanced DER technologies that can produce greater system level benefits? This was a collaboration between the Colorado Energy Office, RMI, formerly the Rocky Mountain Institute, Xcel Energy, and NREL. And NREL's role in this project was to conduct the simulation study using grid and building and grid modeling tools, and to collaborate with the team on developing an experimental plan based on the results. So I'll reiterate that this was a modeling study, and it was kind of preliminary scoping research that was geared toward designing a retrofit energy district. It turned out to be very informative, and we learned a lot of interesting things, as you'll see. The next step is to demonstrate our findings in the field, so we're actively pursuing opportunities to conduct a proper field demonstration. We had two main objectives for our modeling effort, and they're in blue here. One was to characterize the grid flexibility potential and limitations for a range of retrofit scenarios that include both energy efficiency and DER technologies. And the other objective was to build and demonstrate a robust co-simulation platform that can accommodate additional technologies and scenario studies, so that the methods that we develop through this work can be applied to other studies in other regions with other utilities and other building typologies. The graphic here is a schematic outline of our modeling tools and framework, and I'm not going to describe the details of the co-simulation tools because we don't have enough time to do that today. But if you want to dig into how the modeling was done, please feel free to reach out offline. So using this framework, we explored the different retrofit scenarios, including the operational characteristics of the homes in this neighborhood and their impact on the distribution system. We chose the Central Park neighborhood in Denver to base our simulations on. There are a couple features of Central Park that made it particularly attractive for this type of study and for considering this type of retrofit rollout. The first is that the majority of the homes here were newly constructed in the early 2000s, which means that the major equipment like HVAC systems and water heaters in these homes are just approaching end of life. And this first equipment replacement cycle is a pretty unique window of opportunity for a community retrofit strategy, because it might be the only time when the replacement cycle is synchronized across many homes. The other reason is that this is a relatively new neighborhood, so there's a higher likelihood that the distribution infrastructure could accommodate electrification upgrades. So here are the different scenarios we studied and the corresponding retrofit measures applied. So each column is a different scenario. So you've got 1, 2, and 3 across the top. And then each row is a retrofit measure category. Our baseline is the existing mixed fuel neighborhood. So it's based on a neighborhood in Central Park that we modeled. And we selected 3 broad cases that outline the boundaries of our problem space. So scenario 1 here is the conventional retrofit flexibility. So using the BOPT modeling tool, we determine the cost optimal package just based on simple payback of conventional energy efficiency upgrades to apply to the entire neighborhood. So for this scenario, we assume that there are no additional DER technologies, no controls, no PV, and this can be seen as kind of a lower limit to show how much load flexibility is possible in a mostly business as usual case. Scenario 2 is what we call efficient electrification. So here we eliminated the natural gas appliances and electrified each home. And instead of looking for the cost optimal retrofit package, we chose the most energy efficient measures that minimize the annual electric use per home. And we explored this scenario with and without DERs and controls, and these correspond to the sub-scenarios 2A and 2B. And then scenario 3 is electrification without efficiency. So this is a totally different electrification scenario where we just replace the natural gas equipment with electric counterparts without any efficiency improvements. The only energy management strategy here is load shifting, and we're buying the least expensive equipment rather than the most efficient. And this scenario was analyzed with and without DERs and controls, and also with and without rooftop solar. Okay, so here's a snapshot of some results. I regret that we don't have enough time to go into all the details, but I just want to show you what the utility bills start to look like when you compare all these different scenarios. So here are bar charts that summarize the utility bill impacts of the baseline, scenario 1, and scenario 2 retrofits. As a reminder, scenario 2 is efficient electrification. We are using Xcel Energy's time of use rates in our analysis, and the bars are color-coded by end use and averaged across 30 homes. The black line with the dots across the bars represents the net bill, and this is useful for looking at scenario 2B, which is in the lower right, where the solar panels offset the bills quite a bit to the point that your monthly bill is less than 0 for roughly half the year. So let's look at scenario 2A. If I were to show you corresponding graphs plotted in energy units, you would see that the efficient electrification scenario in 2A actually uses slightly less source energy than even the conventional energy efficiency retrofit in scenario 1. But on an annual basis, the utility costs to the homeowners are nearly identical to the baseline because of the higher cost of electric heating in the winter that offsets the cooling savings in the summer. In other words, because electricity is more expensive per unit energy than natural gas under current rates, a conventional retrofit, which is scenario 1, can save money on monthly utility bills relative to the baseline, whereas an efficient electrification, scenario 2A, is approximately cost neutral in terms of energy bills. If you go down to scenario 2B, here we incorporate additional DERs, including a home energy management system or HEMS, the largest PV allowable by the local utility, which happens to be 120% of the previous year's load in the home, a 6 kilowatt hour home battery, and electric vehicles are also added for 1/3 of the homes in the community, reflecting a high but not unrealistic adoption scenarios. EVs represent a substantial load with a higher annual energy use than space cooling, despite its implementation in only 10 out of the 30 homes. And we see that the battery definitely contributes to energy bill savings because of load shifting, because it can perform arbitrage by storing charge during the sunny off-peak hours in the midday and discharging during peak periods. Let's compare this with what we're calling inefficient electrification, or electrification without any energy efficiency measures. And the key takeaway from this slide is that electrification without energy efficiency results in some pretty high electric bills. Scenario 3A in the lower left is kind of a non-starter. Without efficiency upgrades and without any other DER tools, you end up with roughly 40% higher utility bills for the homeowners. Scenario 3B includes some DERs, including a HEMS, an EV, and a battery, but no PV to help power the electric loads. So the addition of EV results in energy use increase over 3A, making this the highest energy using scenario in our study. But the HEMS is able to reduce some energy use for heating, cooling, and water heating by operating at the edge of the flexibility band for comfort. And the battery helps with a little bit of arbitrage. So the scenario has slightly lower bills than 3A despite the overall energy use increase. And then scenario 3C starts to look a little bit better when we add PV to these homes. There are times of the year when this community can export power, especially during the summer months. And homeowners in this scenario still have utility bills to pay, but they're roughly 60% lower than they would be without PV. So I only showed a tiny sample of our results focusing on just the utility bills, but kind of to summarize, here are the most important sort of broader takeaways that we learned through this work. One is that electrification can be achieved without negatively impacting the utility bills. We saw.
They are just reminder we get a one minute warning so we can get to the discussion.
Okay, got it. Electrification can be achieved without negatively impacting the monthly utility bills, and we didn't have time to show the distribution system impacts, but our results did demonstrate that incorporating efficiency can be an important tool to paying attention to key metrics like house level voltages and distribution transformer loading. So electrification of a neighborhood definitely increases the system load and creates some stress. So planning for the distribution system is a crucial component of any efforts to electrify. There are several topics that are kind of interesting for discussion. The cost of electrification, we saw that efficient electrification can save in utility bills, but you have to figure out how technology is affordable. The practice of sizing PV systems based on a home's past energy bills can be problematic when a home also undergoes electrification. So you're adding a bunch of electric loads that you didn't have before. So it seems like those kinds of rules need to change. Evolution of parameters. For peak load management, if you can electrify a neighborhood and still use batteries and PV to reduce the summertime peak load to the point that the community can be a net producer, as long as the surrounding communities are not yet electrified. But looking forward, if the broader system transitions along with the neighborhood, and the entire distribution system could be faced with winter peaks that occur primarily in the early mornings. In that case, the PV wouldn't be able to shift the load in a meaningful way. So these are some interesting things to think about in terms of implications for the relative value of different DER technologies. And finally, in our simulations, the HEMS algorithm based its control decisions on occupant comfort and the cost of energy to the homeowner. In other words, just utility bills under TOU rates. But it would be worthwhile to explore how prioritizing other benefits like carbon emissions reductions might alter the overall energy, the load profile of a home, and the impact of these types of changes on other benefits. I will quit there. Thank you.
Great. Thank you so much, Lega. Thank you to all of our panelists. So now we're going to go into about 10 minutes or so of a moderated discussion. And what I want to do, and this is going to be maybe a little bit selfish, but my company Sealed, we sell to customers every day. So we're talking to people, talking to homeowners every day, trying to convince them to weatherize their home, install heat pumps, install smart controls, all the things that we talked about. So what I want to do is do a lightning round, answers 1 minute or less for everyone. We're going to do a little snake draft. I want you to give me and the rest of the attendees a 1 minute pitch to first give a 1 minute pitch to a homeowner, someone who owns, let's say, a 2,000 square foot home in the Midwest or in a cold area, of what package of technologies they should install and why. Then I also want you to give a pitch to the head of the EPA or some policymaker on why your package of technologies, your approach is the best way to get us to decarbonization by 2050. So we'll do a snake draft. We'll start with the consumer angle with Josh, and we'll go back to the policy angle. So Josh, in 1 minute or less, if you're talking to a homeowner today, what should they be doing to their home and why? What's your pitch to that homeowner, to that customer?
I would say that the first thing they have to do is get an energy audit and aggressively weatherize their home. The basic steps, weather stripping, sealing, air leaks, attic insulation, wall insulation. And I would just reiterate that this is going to bring lots of non-energy benefits. It's going to save them money on their bill. It is cost effective. We know how to do it. We know how to do it really well. And it will set them up for any other investment they want to make on their house and make all those other investments more cost effective. Great. Love it. 30 seconds. You get extra points for giving her time. All right, Jim, you're next up. What technology or suite of technologies should our homeowner, our Jane Smith, adopt?
Yeah, well, I like what Josh said. I mean, obviously, in our science of energy efficiency, getting the envelope right is a good move. It could be expensive and it may not be affordable. So if someone's got like a furnace that broke down and they're wondering what the heck they want to do, and if I can fast forward like 2 years to 2023 and we've got gas heat pumps available, I'd say put a gas heat pump in. It's going to reduce your usage in half. It's going to provide you the comfort that you're used to and that you want. A gas heat pump will produce heat like your furnace. It's hot. It's going to feel warm to your skin. It's going to be comfortable. Last time I checked, when I sign up for my plan with my utility, Nicor Gas, I don't buy therms. I buy comfort, and gas heat pumps provide that. they provide exit temperatures that are above your skin temperature, so it feels warm. They're comfortable, they're affordable, they can fit right in, they're easy to do once we got the trade allies and the products out there. So it's a great solution. Helps save the planet as well, because you're going to be reducing usage by half.
We got you. Appreciate the pitch. Got you in a minute. All right. Leko, what's your pitch to our homeowner, Jane?
I think my pitch would be, it is difficult to make a blanket statement about what technologies any one person or any one home should adopt, because the details of cost effectiveness really at this point depend on the utility rate structures in your area and the rebates available and what else is going on, right? And so, but I would say this, that kind of going along with what Josh was saying, like, if what we learned through this study was that if you are going to electrify, then energy efficiency absolutely has to be part of your considerations. That just because you're adding PV to your roof doesn't mean it doesn't matter how many kilowatt hours you're using. And in the meantime, your home's going to get a lot more comfortable. So do the air sealing, do the insulation, do all those things that seem kind of boring. And I think it will end up being better in the long run, both in terms of cost optimization and just having a better home.
Well, I will say you're in the right crowd. We don't consider weatherization boring here at the AC EEE Energy Efficiency as a Resource Conference. So, but I appreciate the. All right, snake draft. So back to you, Leko. What is your pitch to the head of the EPA or someone who has the most policy power in the country about why they should what approach they should take to decarbonize our homes according to your research?
Oh, that's heavy.
That's why people come to the AC EEE Energy Efficiency as a Resource Conference, right? We ask the tough questions here.
Good question. I think there's still a lot of research that needs to be done on how best we can manage loads at kind of a greater level than just the individual home. So I think there's a lot of work to be done there. I think there are a lot of interesting questions around, there's sort of a chicken or the egg question around sort of utility rate structures, right? And how they can incentivize having different distributed energy resource technologies to help you achieve that load flexibility that you need in order to accommodate 100% carbon-free energy on the grid. So it seems like, I don't know, I guess maybe what I'm saying is it's kind of all of the above. We need to attack it from all angles.
We're at a minute time. Jim, what's your pitch on the policy to get us to full decarbonization in our homes?
I'd say, look, we are fighting the war on climate change, and we need to bring everything to the table. Gas plays an important role, especially in a cold climate, to help us get there quicker, faster, more affordably. It can allow us to bring renewables online quicker. It can allow us to deal with those polar vortexes and those events that occur. It can provide an affordable approach to do that. It can provide a good decarbonization play by introducing RNG and hydrogen and other new low intense fuel products. It's a win-win. It allows us to utilize the gas system as a storage battery, as a huge battery to store when we do, let's do power to gas. So let's take clean electrons flying around, or at the duck curve issue in California, methanize it, put it in the system, you got it on the peak. So I think there's all kinds of resources that we can bring to bear, and we can fight this war and do it better together versus trying to polarize.
Great. Thanks, Jim. A lot of at least polar vortexes in terms of polarization. All right, Josh, finish us off here. What's your policy pitch on how we can decarbonize using your research?
All right, my policy pitch is that we have chronically underinvested in our infrastructure in this country. Our buildings are our infrastructure. We spend most of our time here. Notably, our single-family homes have just not lived up to our needs. We need to focus on improving them. And instead of the temptation of shipping our money away by extracting energy, when you invest those, we need to forward vision to invest that money today to build good buildings that people are comfortable with, recognize that the benefits go well beyond energy savings into quality of life, and just get it done.
Great. Another 30-second answer. You are killing it, Josh. All right. We're running a little far behind, so I'm going to switch over to the audience questions. Thank you, everyone, for submitting some great questions so far. I'm to start. I'm gonna ask kind of a general question that I think applies to everyone that was asking a few different ways. But based on everyone's analysis and their presentation, how sensitive are climate zones or geographies or utility rates? Basically, how sensitive are the local conditions for your analysis or for the technologies that you've been talking about? Basically, like how universal is what you've presented today versus how specific is it to different circumstances? I think I likely know the answer, but I will pass it off to anyone who wants to comment on that.
Well, I'll start by just saying that obviously gas heat pump technology in a cold climate, makes a ton of sense in the way that you can pencil that out, especially in the space heating and water heating situation. As you go south and it gets warmer, that becomes much more challenging. I'd say water heating becomes probably the play, if you will. These technologies soon will include probably air conditioning, so then maybe you've got something else to work with. But I think it's it's a little bit case by case as you start going south. But obviously, when if you've got a weather event that might require our grid to be 4 times the size of what it is today, that just is not going to happen overnight. We need a thoughtful and logical way to approach it. I think like the topic that Josh was talking about weatherizing homes. Yes, we need to do that, but it's going to take some time, and we need to have a kind of a vehicle to get us there in a reasonable, affordable, resilient way to do that. I think gas heat pumps play an important role in that.
Great. Lick, I'm actually going to turn over to you because there is a more specific question around this topic. Is Ross Welterlin is wondering if you took into consideration the reduction in gasoline fuel costs with the electric vehicle charging costs added to the home.
Yeah, so I should have mentioned this, but I was like trying to go at lightning speed. So the net utility bill change was positive, costing I think approximately $100 more per household per year for the houses that had EV. But the increased cost isn't that. Increase was entirely attributable to the inclusion of EV, which is offsetting the gasoline that would otherwise be purchased by the homeowner. And remember, there are only 10 EVs in the 30 house community. And so even if the bill increases all from EV charging, we can estimate that each EV owning household then spends approximately $300 per year on electricity to charge their car. And so in comparison, the annual cost estimate to fuel a gas-powered vehicle that's driven the same number of miles in our modeling was $1,003. So those people would save money, and equally notably, the people that don't have the EVs wouldn't see their utility bills increase. So thanks for pointing that out.
Great. And Josh, from your modeling, how much of this do you think is specific to the areas that you looked versus more universal?
Sure. I would just say that all the results I shared today are based on actually specific building characteristics that we have measured and gathered in Minnesota, specific to climate zone 6 and 7. That said, what I have come to realize, not just from public radio, is that we are all above average in Minnesota. When we do work in climate zones 5, namely Illinois and Massachusetts, we see kind of shockingly high space heating loads there that don't translate into the same building characteristics. That sort of implies to me, though, that we build our homes to the climate, and we have a more demanding climate, so we tend to build our homes better up here. By extension, that means that the opportunities are a little bit better in some of the lower climates than we might just interpolate from results in climate zone 6 and 7. So I think It can extend down into 5, maybe 4.
Gotcha. Okay. Last question before we move to the Zoom. And just as a reminder to everyone, in the chat, everyone should have a link to the Zoom platform that we're going to go to at 2:45, and we're going to have a even more free flowing discussion and dialogue there. So encourage everyone to keep the party rolling over on Zoom. So we are at the ACEEE Energy Efficiency as a Resource Conference. We all got to put our cards on the table when it comes to energy efficiency. A few questions came in relative to what the actual efficiency levels are going to be and what that looks like, apples to apples, because this also plays a part, right? Not just in convincing customers and looking at the market trends, but also as it relates to things like Energy Star standards, regulations, and performance standards in the future. So I'm going to start with you, Jim, because a couple of questions came in for you on around this. And they're kind of related, which is both for heat pump, gas heat pump, water heaters, as well as for gas heat pump, heating and cooling technology. What is the apples to apples efficiency levels? Specifically, I think you had mentioned that heat pump will reduce consumption by about half, but that the increase in efficiency is I think 130 to 140%. So how do you have that math kind of come together? And then for Josh or Lieko, whoever, one or both of you want to go, what's the equivalent in terms of efficiency? So if we're talking apples to apples of all of these approaches here, and we can include weatherization in the total efficiency, what are the total efficiency levels we think we can get to compared to the current state of affairs?
Sorry. Great point on that. The 197 to 130, 140%. That's right. If you do that math, maybe it's not 50%. But two points. One, if we're doing retrofits and we're retrofitting existing buildings, obviously we're probably going to be touching a lot of furnaces that are not condensing units, right? They haven't put those in yet. So I think there's, if you look at the true usage, you're probably got a pretty significant change. It's a significant step change. It's not nibbling up from like a 95 to get a couple more percent to 97 to 98. I mean, this is a big change. So first of all, there's a pretty significant change in furnace technology here. For water heating, same way, that 0.62 energy factor to a 1.2 energy factor, big step changes. And so I think those are real. These units have been tested. They've been out in the field in the last 2-3 years and have been in negative 20-degree temperature kind of climate, and they have performed. COPs above 1, and especially for that combi space heating unit, you'll never get below like the 97. So you always kind of be at the condensing level. So I think it's a big change. It's a significant change. You can't discount that. My numbers might not be exactly right. I probably said that too much off the cuff. But and then there was another question about the, I don't know if you want me to take this, about the water heater Energy Star criteria at 1.0. Yeah, that's just right off the hot off the press, right? So what does that mean? Well, if you look at that standard, it looks to say that basically, if that goes into play, that would mean in 2023, you're basically looking at heat pump technology to do water heating. What's the problem? That's about when those technologies are going to be coming to market. So I feel like it's a little tight. It would be nice if they could add another 6 months or so to that. I think when the electric heat pump came out, they had a pretty tight timeline as well. The market responded. There are a number of manufacturers that have products in Europe, have products in Asia. They are all trying to get into the market. There's maybe 4 or 5 that I am aware of, 6 maybe, that are looking to try and get into the market. So it's just a matter of time. They're going to be here in the next couple of years.
Okay, great. Thanks, Jim. We're gonna little teaser. We're gonna continue this discussion in this question over on Zoom. So again, please everyone go to the Zoom link that you have. I will stay on this. So if anybody has any questions or isn't sure about how to do that, please send in your questions, and we will see you over on Zoom very shortly.